What up, everybody? Welcome to another live stream here on Master the NEC on YouTube, as well as over on Fast Tracks Tube, our proprietary platform where you can also watch these live shows every week at 8 a.m. Eastern Time. And so thanks for joining me today. So today's episode, we're going to be talking a little bit about transformers, and we're going to be working out of our Fast Tracks program. So for those that are out there that have our Fast Tracks programs, we're going to be in Unit 14. And this kind of moves you past the normal stuff where we do exam prep, where we're preparing calculations, right? So Unit 8 is single family dwelling, Unit 11 is multifamily, and Unit 13 is commercial calculations. So for anybody out there is wondering what's actually in the Fast Tracks program, most certainly are going to be dealing with calculations and filling out different forms to get you familiar with calculations. But now, when you get into Unit 14, we start moving into the little things like transformers that can help you understand transformers a little bit better, let you know the different types of transformers. And then we'll talk a little bit about probably, and we'll obviously have other episodes on transformers for your morning drive. But today we're going to kind of focus on the overcurrent protection for a transformer, realizing that the overcurrent protection that we're going to be talking about is for the actual transformer. Now, it may serve double duty, and it may also protect the conductors, depending on how you size everything. But its primary focus is really to make sure that we are attacking the overcurrent protection. Right? That's the key focus that we're going to be working on today. And I noticed really quickly, let me move something here. Okay, sorry about that. So let's go on and get into today's show. And I should mention today's show is sponsored by Electrical Code Academy. Obviously, that is the academy where you can get courses on exam prep. But we do have some shout outs this morning. Alfonso is joining us. Thanks for joining us, Alfonso. Let me know where you're from. And then we got Richard. Good morning. Anaheim. Way out there on the West Coast already this morning. Early on there. And we got Edgar. Edgar joining us. Good morning, Edgar. Thanks for joining me today. So I did tell everybody that the next live show would be Thursday. We try to do these every morning. And so I made a commitment. I said, you know what? I'm not going to do that. I am going to make sure that we are live and be able to, what is it? Let's see here. Alfonso is from Pomona. Is that California? I'm terrible with geography or things like that. So anyway, welcome to the stream. And again, if you have any questions, please feel free to post them in the comments. I will do my best to answer any questions. So this is just a recap in case you missed the first episode. This is where we're going to be doing the live streams, and we selected YouTube, and we've selected our own proprietary platform, which is over on Fast Tracks Tube. So you might want to check that out as well. There is a slight delay. I don't know if it's a delay on YouTube, but there is a slight delay over there because of how our system processes it, that type of thing. Good morning, Red Dog. Thanks for joining me. I have my coffee with me, folks. Again, I'm just going with the Dunkin' Donut blend, and our coffee is on the way. So I have gotten confirmation that my new roast is on the way. So excited about that. It's a bit costly. So anyway, all right, let's go on and talk about today's topic. So I'm going to share you over and get you into our program. So let's go here. So here we are. We're in the program. For those students that are really familiar with this is Unit 14. We're talking transformers. Transformers are indeed separately derived systems. It is basically, when you have a transformer, you have what's called a primary winding and a secondary winding. They do not touch, okay? They're close, but they do not touch. So they have a separation that separates the primary to the secondary, okay? And so in that separation, we have electromagnetic induction that transfers power from a primary to a secondary. Now, as far as the grounding and things like that happen, the grounding is intimate with the primary to secondary, okay? Because you have to bond all this stuff together. They come together on a common terminal block, okay? And so in that scenario, you want to make sure that that you got your primary and your secondary. Again, if they were to touch, then it would fault out. So that's all built in the transformer. Now, when it comes to transformer protection that we'll be talking about, and Alfonso, I see your question. It looks a little bit detailed for me to take up our time today for transformers. That's your questions generally we like to be germane. I encourage you to send that question over to paulabernathy.com because I'd have to look that up. Elevators are definitely auxiliary contacts. All that stuff is certainly not in my daily knowledge thing. So you're probably going to have to send that in so I can look it up for you and give you a little more detailed response. Probably not. It would derail this whole show if I got into something like that. So apologize. I did say you asked questions, but that seems like a very detailed question on an installation, not so much code. So definitely send that into paulabernathy.com. All right. I really don't want to derail the show. That's why. So, all right. So if you look to here, we'll be dealing with Article 450 of the National Electrical Code. And what we're going to be looking at, again, you have current transformers. We have dry type transformers. So to tell you, Alfonso, there's a high probability our Fast Tracks program will not answer that question for you. That is very specialized. So for those out there, just to recap, our Fast Tracks program is to teach you what you need to know to pass an electrical exam. It does not cover all of the NEC. So again, you're not getting a program that's going to cover every footprint of the NEC. It just would be too impossible to do that. So I just Alfonso, because I always like to be good stewards of people's money. Question that you see right there, you will not find in the Fast Tracks program. I promise you that. Transformers, okay, are very common in machines like X-ray machines, high-frequency machines. Transformers also can be something as simple as a Class 2 or Class 3 type transformer or circuit, which, again, are going to have limited voltages, so it's voltage limitations. Think of those more like a Class 2. Kind of think of that as like a doorbell circuit, okay? That's a transformer, okay? All right, so we're going to try to cover, and again, we're not going to be talking about auto transformers, okay? But we do reference them here in our program. An auto transformer, even though it has transformer in the name, it is not a separately derived system because there is intimate contact between the primary and the secondary based on where the tap is located. So that is not really a separately derived system. Okay, so we're going to try to stick with just transformers today. All right, this just happened to be an example of, so this is an oil transformer. This is a dry type transformer you're probably more familiar with. Okay, that type of scenario. And as you can see, we have the call outs. Okay, and you have single phase, you have three-phase transformers, you have three-phase transformers that are configured by connecting certain configurations of single-phase transformers. All those type of things. What we're going to be focusing on is right here in just not going to do anything with the over 1,000, but we are going to focus on those tables. So 450.3a, that's for over 1,000. And then we come down here, and we're going to be also focusing on 450.3b, which is dealing for what? Under 1,000. So real quick, let's go to the NEC really quick. So here's where we're at in the National Electrical Code, Article 450 for transformers. We're not going to be talking about transformer vaults. Okay? We're just talking about general for transformers. And what we want to spend our time today is talking about the overcurrent protection. All right, so overcurrent protection as it is to the transformer itself. Now, as we said before, or as I've said, is it possible in order to provide the overcurrent protection or the protection to the conductors involved in the application? Yes, It is totally possible for that, but it's all about sizing and making sure that if you're going to use a table and you go up to, for example, the allowance where it says you can go up to 250% on the primary, that you want to make sure that if you did that, you're not leaving your conductors unprotected. And if you don't increase the size of conductors and you just go up to make sure that those conductors are protected by the overcurrent device, then what's going to happen is well, first of all, you're doing conductors that are larger than necessary. So you're spending undue money to do that. You don't need to spend that kind of money in order to still follow all the rules within the NEC. Okay? So that's important to understand. So as we look at the protection, let's focus real quick on disconnecting means first. Let's kind of draw this layout together. So let's talk disconnecting means for transformers. All right, so we're talking transformer other than class 2 and class 3 transformers, which you typically, what you're going to see is like a class 2 is going to be a doorbell transformer. I don't think we need to worry about a disconnecting means for that. We have the protection on the primary side and we all the way up to the breaker that's supplying that circuit. Okay, so that's not an issue. And then typically that's going to be like a 120 volt, or since it's more of a power circuit than what we would get on the secondary side of these little transformers, these class 2 transformers, for example, which is going to limit it. And so you really wouldn't put any protection to that. And you all are familiar with that. You go right to the doorbell. You don't need to have anything on that. Now, other than those type of small little transformers shall have a disconnecting means located either in sight of the transformer or in a remote location. Now, when it's in a remote location, and I'll show you an example of a picture, if it's in a remote location, then that disconnect has to be lockable in accordance with 110.25. And what is that? That means lockable in the open position. So that means I can have my transformer. Typically, I have the disconnect for that transformer within sight. Okay, we know in sight's within 50 feet and visually in sight. But the code does allow for it to be remote. It means it's not visible from the transformer. However, there's things you have to do if you want to have that kind of installation, right? And that's when it says that it needs to be field marked. And again, in our program, you see these little chevrons. These little chevrons are basically to tell you to stop and go to the NEC. So for example, 450.14, if we were to go to that, and I'll share this for you, here's your transform. Here's where it's talking about the disconnect. And it's pretty much verbatim, exactly how we put it in the program, right? So transformers, and again, we're not talking about these types. Transformers in general shall have a disconnect means located either in sight of the transformer or in a remote location. Where the location is remote, the disconnect shall be lockable open in accordance with 110.25. Okay, so here you see some additional commentary, all right? In case you need this additional commentary. All right. So let's go back here to the lesson. All right. So we have to have that disconnect. Now, what do we mean by marking and it needs to be field marked? Well, now we agree that we have to have the disconnect. Okay. And it says each disconnecting means shall be legibly marked to indicate its purpose unless located and arranged for a purpose is evident. So what that means is every disconnect now in 110.22a says that you have to say, if I have this disconnect, I need to know where it goes to. Well, this is saying, this transformer disconnect, if it's located right beside the transformer, then that's obviously, you can see the raceways going over to it or cables going over to it, whatever. It's obviously associated with that transformer. So it makes the markings unnecessary because it's very evident what these disconnects are controlling, okay? Now, also durability. One of the things to be aware of is that sometimes the locations, the labels cannot be as something simple as an inkjet, things like that. It has to be something that can withstand the environment for long term, whether it's a phenolic label, whether it's a plastic embossed, however it is you buy, it needs to be very evident of the location, and it has to be durable. Now, also you can see the call outs down here in our program. So A, for example, you you've got all these call outs. So here's A, just showing you talking about the labels and within sight and all this. So obviously this disconnect here is within sight. Okay, not a big deal. This is an example of where it would not be in sight. Okay, so it's running through and it's in another room. And so it's not here, but here's that label. And that is telling you where this transformer's disconnect is located. All right, so here it's in the gear. So put this label on there. And this is an example of a phenolic label. Okay, it says there's plastic ones where it actually gets embossed or etched in or carved into the plaque, and that gets mounted onto it. And that's going to tell whoever's here, they know exactly where to go to disconnect this transformer for servicing. Makes sense. This is a rule that expanded a couple cycles ago, and it makes sense because, again, y'all will be working on it, and you might not know where, or you might have a building that's so substantial that there's so many different rooms of power, equipment rooms, that you do not know where to turn off this daggone transformer. And there's no need to work on any of this live. Okay, so got to have the ability to know where to do that. Next is C. C is calling out here, right here. Okay, and this is lockable in the open position in accordance with 110.25 because it is not within sight. All right, so that's what this is. Okay. The other thing about this lockable provision, let me go in and highlight that. So under 110.25, and again, you should stop and go to your code book on 110.25 and look at it. Lockable in the open position, that needs to stay in place, whether a lock is installed or not. Now, in these here, it's pretty easy because usually these have a little setting in a metal loop or a tab. So again, it doesn't matter. It could be whether the lock's there or not. It could be, it's not only when a lock's in place. Right? So those are pretty much, a lot of that gear is already built in. But you may have a situation on a panel board, in an enclosure with a panel board in it. You may have a situation where it's not that. And so you have to use the type that will stay whether a lock is installed or not. So it usually will mount on the actual cover that goes on top of the equipment, that type of thing. So that's a key thing to remember in that provision. And again, D is just reminding us the label as we said before. Okay, so that's that disconnecting means. And this is on the primary side of the transformer. So that is just the disconnect. Right? That is not providing any overcurrent protection. That is simply the disconnect rule that's required for that. Okay. All right, now let's talk a little bit about transformers and the protection for the overcurrent protection. All right. So first thing we'll look as a transformer. Now I got to give you context to the code. So we'll go to the code real quick. And we're going to look at this protection. We're going to go down to 3. All right. So we're doing, let me make sure that I'm doing the right one. Yes. Okay. Right here. So let me share this screen. All right. So here's what we're looking at. All right. And I want to bring the context to it. Let me see if I can make it bigger. All right. That's good enough. I'll move where I need to move. Okay, so this first one we'll be looking at is that you have primary only protection. So you have this transformer, it's rated 1,000 volts or less. You're gonna be going to this table, and that's probably the majority of the transformers that you folks are gonna work with, okay? 1,000 volts or less. If it's over 1,000 volts, then you just go to 450.3A and utilize that. But this is the majority of the transformers you're gonna deal with, all right? So as it says in the lesson, all right, so if we have a transformer with primary only protection and it's 9 amps or more, that is going to be the vast majority of the transformers that you folks will deal with, okay? All right, so let's kind of read a little bit into this. It says, and this is right out of our program, it says conductors supplied by a secondary side of a single-phase transformer having a 2-wire single voltage secondary or a 3-phase delta-delta connected transformer having a 3-wire single voltage secondary can be protected by overcurrent protection situated on the primary side of the transformer, provided the protection is in accordance with 450.3 and does not exceed the values determined when multiplying the secondary conductor's ampacity by the primary secondary to primary transformer voltage ratio. Now, where do we get that from? So that's a allowance in 240.21c1. So that's the one where you're basically, if you're dealing with a transformer that is a single phase transformer and it's only a 2-wire secondary, or a two-wire single voltage secondary. So all it does on the secondary is produce one single phase voltage, like a 120. That's it. Okay. Now, and also the next thing would be, also applies if you're doing a delta to delta 3-phase, having only 3 wires. If that's the kind of output you have for the secondary of that transformer, then basically it's saying what? That you can have the primary only protection and you don't have to have any secondary protection for that transformer. That's all it's talking about, okay? All right, so let's kind of look. So here's what's kind of give it a look, see what we've got going on here, and you'll get a bigger idea. So here's our layout. So here's our, notice you says not required, okay, in this setup here, if you follow all these rules, okay? So you got to follow all these rules in order to be able to have primary only protection, no secondary protection for this transformer, just primary only, all right? And again, I will tell you, this is 99% of the time, this is not how you're going to do it. This is not what you're going to use. You're going to be using 240.21C2 or C3 or C4. Okay? You're going to be using the 10-foot rules. You're going to be using the 25-foot. You're going to be using the outside unlimited rules. You're not going to be using this application right here, but we need to talk about it. So if you have that unique situation. Okay, so now, where 125% of this current does not correspond to the standard fuse or an adjustable circuit breaker rating, the next higher rated, and that's described, all the breakers are listed in 240.6, is permitted by note 1. So let me show you what it's talking about on the code. So here, this is what it's talking about. See how this is 9 amps or more. See this little note right here? Oops, I'm not sharing it. See this little note right here? That little 1 right there? So that little 1, and remember, we're not doing secondary protection for this transformer. We're just saying, can we protect the transformer by the primary protection only? Can we? And the answer is yes, if you meet all these rules. All right, so that here's where it states, well, if it doesn't correspond, then you can go up to the next standard size. Okay, so that's an example. If we calculate this out, we take the transformer's current and we do it at 125%, and it doesn't meet exactly on a breaker that's listed in 240.6, then what does that mean we can do? Well, that means we can go to the next standard size. So that's what that little note is telling me right there. Okay, so again, remember, this is primary only protection, okay? And it's for the transformer, not protecting the wires yet. We're just talking about for the transformer. All right. Next, this represents either, and this is a caveat, to do what we're doing right now to have no secondary protection, this is the caveat. It has to be either a single phase transformer having a 2-wire single voltage secondary, only 1 voltage option on the secondary, not like a 120, 240, only 1 voltage option, and it has to be single phase. Or you can also use this protection scheme for the transformer if it is a 3-phase delta-delta connected transformer. Okay, so it's got to be 3-phase. It's got to be a delta primary, a delta secondary, only 1 single voltage on the secondary. That may be like a 480 volt delta. Okay, be like a 480 volt corner grounded delta. You only come off with 3 wires. It's a 3-wire secondary, and it's going to produce 1 voltage only. If that's your situation, this is what I want to emphasize. If that's what you're doing and you want to protect that transformer with only primary protection, you don't want nothing on the secondary for protection, this is the kind of system it has to be first. This is the first one, okay? Very key and critical that you understand that. Okay, now, D, okay, and we're talking D right here. D says single phase other than 2-wire and multi-phase other than the delta we've been talking about. So this would be every other transformer, okay, that's out there, not those unique ones, but the normal ones you probably deal with every day. With those, the transformer secondary conductors are not considered protected by the primary overcurrent protective device. Okay, so you can't have primary only protection in your scheme, whether that is protecting the transformer or you're protecting the conductors, primary or secondary. In that same scheme that we were talking about, if you're dealing with all other types of transformers, the normal ones we deal with, then you're going to have some type of secondary protection to protect not only the transformer, but also to protect conductors. So you have to think about that in your design, okay? And let's see here. Overcurrent protection for transformers, again, what we're talking about, rated 1,000 volts nominal or less, must be provided in accordance with 450.3b. That's kind of what we've been talking about. Unless the transformer is installed as a motor control circuit transformer in accordance with 430.72c1 through c5. And that, again, if you're dealing with a transformer that is integral to a motor control circuit, then, again, you ignore this because typically that's all designed into the system itself. Okay, so you're not dealing with that if you're dealing with some type of transformer that's integral or part of our motor control circuit transformer, okay? Now, F, and I'm not sure the call out here, E, okay, it's just general. And then, of course, this transformer that you're looking at right here, this transformer is a three-phase delta-delta connected transformer. It only has a three-wire voltage, a single voltage secondary, okay? So, again, that means this is a delta-delta, three-wire coming in, three-wire going out. Another question that people ask, do I still have to do the grounding, and do I still have to have equipment grounding conductors, or do I still have to have all the grounding as I would with a normal transformer? Absolutely you do, okay? But you don't have a neutral generated here, right? So you don't have that in the system. But in order to do that, if we say that this is the case, it is a three-phase delta to delta, then we only have to size the primary protection at 125%. Okay, so if this was, you did the math and you know what the VA is on this, or the KVA is, and you're dividing about whatever the voltage is on the primary, let's just say it was 60 amps, just throwing a number out there. You do 60 times 1.25, and that's 75 amps. So the maximum that you could have is 75 amps primary protection, unless, of course, it didn't correspond with a standard sized overcurrent device. Then you jump up to the next standard size. Okay. The key thing to remember here in all of this is that this right here is only the scheme primary only protection, and I'll show it here again. This scheme is only going to be can do this if you're doing primary only protection, okay, and you follow all of the rules. Then you can protect the transformer with primary only, and you can protect the secondary conductors with primary only protection. Very unique in that scenario to those type of transformers. Again, I just want to make it very clear. Got to be a single phase, two-wire secondary, or a three-phase delta to delta three-wire secondary and primary in order to be able to use the 125% protection without any secondary conductor protection. Okay? Just want to make that clear. Also, there is an important notice, and our program does this all the time, is it gives you warnings and cautions. And it reminds you, although table 450.3 does not require secondary overcurrent protection for all transformers, like the one we just talked about, you got to remember that if this happens to be feeding a panel board, that 408.36b requires secondary overcurrent for most panel boards, okay? So where the panel board is supplied through a transformer, locate the overcurrent protection on the transformer secondary side. Typically, that's going to be either in a main breaker, right? That you're going to have that scenario. That's typically what you're going to feed into, okay? So just keep that in mind, even in this scenario. Now, let's talk about other than that note one, that special application, right? So we're going to talk about where you have primary and secondary protection for 9 amperes or more and 1,000 volts or less. So this is probably the reason I showed you the other one first, because that is a rare installation. And I want to make sure that you're clear when somebody comes to you and says, hey, can I have primary only protection for that transformer in those conductors? Your mindset is, yes, it's possible, but I have to have a unique type of transformer. Again, single phase, 1 voltage output, or 3-phase delta delta, 1 voltage, 3-wire output. Can't be a 120, 240. There is no neutral involved in those. If that's the case, you follow all the rules. Okay, 240.21c1, you're good to go. Here's the other rules. Okay, so now we're going to be looking here. So this is what me and you'll probably deal with on an everyday basis. We're talking about transformer protection and everything involved with primary and secondary. Okay, that's what we're going to be dealing with right now. Okay, number 1. All right, let's look at this transformer. So here's the first one we'll look at. So in this transformer, this one has primary and secondary protection. And you'll notice it says 250 right here. Okay. All right. So let's look here. It says, first thing we look at is note A. A is pointing right here. It says, unlike note 1 that permits the next standard rating above 125%, the maximum rating or setting is 250%. So what are we talking about? Let's go to this tab. So right here, if you happen to be using this, okay, scenario right here, then you have currents of 9 amps or more. That's your transformer's output, 9 amps or more. Then you can go up to 250%, but you cannot go over that. That is a maximum. Now, you do have a note 3 right here that talks about unique types of transformers. These are transformers that have a thermal overload protection built in by the manufacturer. I have not encountered but one of those. And even then, it then gives you some values that you can work with down here, whether it's 6%, not more than 6% impedance, and that type of thing. Or you can also have another scenario where you have a transformer where it's 6%, but not more than 10% of impedance. So it depends on your transformer's rating. So you have some allowances down here, but I tell people, look, generally, if you're going to do this and you're going to have the primary protection, okay, then you're going to have, you cannot exceed 250% on the primary. Now, this brings me back to one question that people ask. Do I have to have, I know I can go up to 250% on the primary. Do I have to? Do I have to go all the way up to 250%? And the answer to that is absolutely not. You do not have to go. That's a maximum rating. Most design professionals are not. They're going to go to 125% on the primary, right? And do the same thing on the secondary. And because if they do 125% on the primary side, then they can also ensure that they're going to protect the conductors, because if they size the conductors at 125% on the primary, then the overcurrent protection for the transformer can also serve double duty and protect the conductors as well on the primary. So that's why, if you ever wondered why you do that. Okay. Now let's continue down. Let's look at B. So B call out is a transformer. So it's saying a transformer equipped with that coordinated thermal overload protection. Again, that's manufacturers installed and arranged to interrupt the primary current can have a primary overcurrent protection rating or set at a current value not more than 6 times the rated current of the transformer. If that transformer is having not more than 6% impedance, and not more than 4 times the current rating of the transformer, where it has more than 6 but not more than 10. So you do have some leeways and allowances here to be able to utilize. And the reason we bring this up is because it could be that these values exceed the 250, and the maximum was 250. So you have that note, which is kind of like the next size up rule, but it's not. It says, okay, well, if that 250 is not going to work, then go check out the notes. And depending on your impedance, you may be able to get away with something, okay? Be able to do something else because of the inherent nature of the transformer. So that's all that note is about. Now, C, the C here is, again, this is pointing to the transformer. So it says overcurrent protection for transformers rated 1,000 volts nominal or less, that's what we're dealing with, must be provided, that's the overcurrent protection, in accordance with 450.3b, unless a transformer is installed again in a motor control circuit transformer. Okay, then you have your own rule for that. So if you don't know, it's just a standard transformer, you'll probably know if it's a transformer that's associated with a motor control circuit application. Then you'll know. And then you just go to 430.72, C1 through C5, and apply the rules accordingly. But we're just talking about just a standard transformer. Right? Nothing special here with it. And it shows you that you have to provide that protection. Okay. All right. In this case, we're doing it with this 250 on the primary, but we got this 125 on the secondary. Next, D, point it right here. So where 125% of this current does not correspond to the standard fuse or non-adjustable circuit breaker, the next size rating described in 240.6 is permitted. So we get this rule right here, whereas this one you can't exceed 250%, primary side, but you got the note you can go to, but it's not the next size up rule note. It's very specific. Here, the secondary is allowing you to use the next size up for that. So that's where you come over here, and right here, secondary protection. And here you see the 125%, but it's got this little 1 right here. And this little 1 right here corresponds with this note right here. So if you kind of come up with a voltage that's not listed on the tables in 240.6, then you're like, well, what do I do? Do I go down? No, this note says you can jump up to the next standard size. Okay, that's what that note is trying to let you know. So in this scenario right here, how would I protect this transformer and protect these conductors? And here's where it can get tricky. I can go up to, so this was say this was a 75 kVA transformer. Okay, say it's 75 kVA, and it's 480 volt primary, right? So that I'm going to go 75,000, and also since it is 3-phase, I got to do what? I got to determine 480 times what? 1.732. Remember, so I got to do 480, and that gives me 831.36, right? So then I'm going to take that 75,000, and I'm going to divide that by 831.36. And that gives me 90.21 amps. So I've got 90 amps here, and I can do the protection up to 250%. So that 90.21 times 2.50 is 225.5 amps. So I'm going to put a 225 amp protection on the primary. I'm going to make sure that that protects these conductors. Okay. And then on the secondary side, that same type of transformer. Now this would be, let's say it's a secondary is a 12208. So in the same scenario, I'm going to take that 208 times 1.732. That gives me 360.25. And so let's just take that, and I'm going to do 75,000 divided by 360.25. If you want to just use 360 to get you in the ballpark. And that's 208 amps on the secondary. Okay. So I have to, now that's not going to correspond with a breaker, right? And for 240.6A. So what am I allowed to do? I'm allowed to go up to the next standard size. Okay. So if I were to go to the NEC, right? And I were to go to 240.6, I'm going to take you here just to show you which we would be at. So it would be 240.6. Oh, kicked me out. Guess it didn't like me this morning. Link will sometimes kick you out. So let's go here. 240.6. Right here. So here's your standard sizes. Okay. And we needed 208. Well, 200. So again, so this would be a maximum would be 225 on this secondary. And if you follow those rules, then everything is okay. Of course, these secondary conductors, again, you're going to have to protect those because of how they terminate. They cannot be less, and you can't use the next size up rule on these conductors. So they have to be sized at least whatever is the device that they're terminating into, whatever the rating. So it'd be 225 amps. These conductors would have to be rated at least good for 225 amps. Makes sense? Okay, grounding and so that is basic. So what I want to do is take you back really quickly to table again. and show you some protection schemes when it comes to conductors. Because again, it's really as simple as we've looked at. It's not complicated. But you have to protect the conductors as well. We know that. So this rule right here was simply to protect the transformer. But we still have to protect the conductors, okay? So on that primary side, right? And when you look at the primary side, we're like, okay, I have to protect those conductors on the primary side. And if I'm terminating those into a, let's say it was a 250%, then I would be sizing those to terminate into a, so they have to have an ampacity that's good for at least that. And so I would go to 31016 and find a conductor for that ampacity. Now, the reason that people would ever go to a 250% primary, there's only one real reason why you would do that. And that is if your transformer is coming off, your panels, these are being fed from a panel, and it's a feeder, and you're feeding multiple transformers. If you're feeding multiple transformers, then what happens is you can the going up to 250% makes sense, okay? Because the application would be you don't want any one transformer to cause it to trip, and so you're allowed to go up to a higher rating, and it makes it a little more palatable for the system if you go up to 250%. Most of the design professionals, and let me know in the comments if you worked with this, most of the time, even though you could go up to 250%, they don't go up to 250%. They typically, if it's just a single transformer installation, then they'll go up to 125%. And then they'll size the conductors to 125%. So that same transformer that we were dealing with, that 480 transformer primary, we'll just do it at 75 kVA. So 75 kVA would be, so let's do 480 times 1.732 again. So it's 831.36. So 75,000 divided by 831. So 75,000. Oops, calculator's messing up. Divided by 831.36, again, was 90, right? 90.21. So I'm going to take that. I'm just take the 90, keep it simple. I'm going to do 90 times 1.25, and that's going to be 112.5, okay, for the primary protections. This is typically how you would do it. You wouldn't use the 250. Even though it says that's the max, most people don't unless you're going to have multiple transformers on feeders. So typically for you and me in the installation, it's going to be 125%. So let me show you why. So now when you go look at the code and we say, okay, well, what overcurrent device are we going to use for that? Okay, so when we go to that, we're going to go 240.6 for that. And we say, well, what are we going to do for that? So we're at 112.5. So 110, so we're going to go up to 125. Okay, so that means we would have a 125 amps on the primary protection, right? And it's a disconnect. So we got the disconnect. Obviously, it's next to it, so we don't have to label it. It's evident. We put in the fuses or whatever you want, the circuit breakers. This is at 125 amps. Now we're sizing those conductors. Well, what size conductors would we use? Well, at that point, we're going to go to 31016 and see what size conductors we'd have to have. So 31016 right here. And we're just going to pop this out so you can see it. And I will share this. So here it is. And okay, so in our case, we're obviously over 100. We didn't say the conductor type, but we're saying all the terminals are rated 75. The wire is going to be a THHN/THWN-2. So meeting all the rules in 110.14c, we're going to be in the 75-degree column. And we need to have something that's going to be good for, that's going to terminate on that overcurrent protected device. So in this case, I would do a 1 gauge copper, that type of thing. All right. All right. Hopefully that makes sense. Anybody have any questions on transformers? I know I went over pretty quick, and I had to realize that I'm doing this in an hour. So I wanted to make sure I covered things that I think are pertinent to it, to try to cover it. So let's go down real quickly. If you got any questions about transformers, go ahead. Let me get just down to show you some of the bonding aspects of this type of thing. Okay. All right. Well, and again, post your questions if you have any questions on the topic. All right. So grounding and bonding terminations in a panel. So premise wiring is defined as interior exterior wiring, including power, lighting, control, and signal, together with their associated hardware, fittings, and wiring devices, both permanent and temporarily installed. This includes wire from the service point or power source to outlets, or from wiring from and including the power source to the outlets where there is no service point. Such wiring does not include wiring internal to apparatus, luminaires, motors, controls, motor control centers, and similar. So we're not talking about the wiring inside of an apparatus or piece of equipment. That's already evaluated by the manufacturer. No sense in recreating the wheel. What we're talking about is the other sources of power that's coming in. All of that's coming in is from an outside source. That's either part of the premise wiring, whether it's interior, exterior. Okay. So what I wanted to show is a transformer, because a transformer here is separately derived. And this is what we're looking at as a normal grounding scheme. So here's your primary side right here. You see that an equipment ground still runs with it. No neutral provided here. Okay, this is primary side. You see it's coming in. And because the color scheme is not required, this is obviously looks like this is 480 volts. But again, it's not, this color scheme, people think that brown, orange, yellow, or whatever is all required to be for 480. That is not true. That's not in the NEC anywhere. That might be in your standards, your drawings. That might be what the engineer specifies. That might be in a local rule that you have in your jurisdiction, but it's not in the National Electrical Code. Okay. All right. So we're seeing this right here coming down, and it's using flex because of the size of this flex. Okay. Here you see it coming down, coming through, and bonding to the enclosure. And this is a punched hole, by the way. This is not concentric or eccentric. It's total punched hole. Okay. Now, we do get good call outs for E. E says the size of the equipment grounding conductor in accordance with 250.122. Okay. The equipment grounding conductor must be the type listed in 250.118A. By the way, this EGC that's being run with it is sized based on the overcurrent protection that's supplying the circuit. Okay. That's what this is based on. And again, this right here is, if this was like for an FMC and that type of thing, depending on the size of it, you may have to bond it. Or if these fittings are all listed and this is a punched hole, it's not a concentric or eccentric, you actually cut this hole, then it may or may not be necessary for any type of bonding bushing here. Okay. This depends. And then over here on the secondary itself, you see right here, the normal color scheme tells me this is a 12208 going up here. And you see F is called out, right? And it says if the building or structure is supplied by a feeder from an outdoor separately derived system, then a system bonding jumper at both the source and the first disconnect mean is permitted. Okay? So what that means is if your transformer is coming from the separately derived system is outside, then you have the allowance to be able to do the system bonding jumper at either both, okay, locations. Again, as long as you're not establishing a parallel path and create that issue with it, okay? So you can't have that. So most people will choose the location on where they're putting their system bonding jumper in order to ensure that we don't get parallel paths, create that problem, okay? Right, so anyway, this right here is your supply side bonding jumper, okay? It's coming up. And then you got your here, they happen to be the, right here, happens to be the system bonding jumper done right here, okay? And I don't see that done here, okay, in this transformer. So here you see bonding jumper is not installed. So you have a choice to do it here, or you can do it here. And here you see there's a screw in here. So this is in here, okay, that type of thing. And we won't get into all of the grounding schemes. We'll do that on another episode. But I just wanted to show you an example here of where the system bonding jumper is being installed here at the transformer. and it is not installed here. So this would be an example of this. This is an example of it's where it's being done at the first disconnect right here. And this is an example where it's being done in the actual transformer right here. Okay. But you'll notice if it's done here, it's not done here. Okay. Because doing so would create parallel paths on this scenario because we have this metal flex here, right? And so, and the other key thing to remember is on this separately derived system, your grounding electrode conductor for this system, and follow all that in 250.30, you will notice that if your system bonding jumper is installed here in the transformer, that is where you go out to the electrode. All right? That's where your grounding electrode conductor will leave from. In the previous one, you'll notice that it was done in the panel. That is where your grounding electrode conductor will leave, right here in the panel. So again, wherever you choose to have in your transformer setup, wherever you choose to have your system bonding jumper, that is the location that you're also going to have the wherever your system bonding jumper, that's where you're going to take your grounding electrode conductor out of. Okay. Yeah, Alfonso says it's good to know he goes off color coding, and you know it may be something that your jurisdiction requires. It may be written somewhere, but it's certainly not in the NEC. The only things that are in the NEC that are colored specific is the neutral, which has to be white or gray, or any color other than green with 3 white or gray stripes, color specific, right? You have equipment grounding conductors. So if the equipment grounding conductor is insulated, then it will be green. And if it's 4 or larger, then it could be black with green tape, that type of thing. But it's also, you have isolated grounds, it can be green with yellow stripes. But you have to remember that if it is smaller than 4, then it is green. Now, does that mean everything has to be green when it comes to equipment grounds? Obviously not. You have non-metallic sheet cable, it's bare. So bare is okay as well. And you can have a bare equipment ground inside of a sheathed cable. And you have some applications of that as well. But when it comes to the color schemes, there's nothing in the NEC that demands those color schemes to be utilized. But again, in all fairness, it could be something that your engineer specifies. It could be something that your locality has in their rules that they've adopted somewhere. Just make sure that they provide you that information in writing, right? Just because we want to make sure that they cover that. Also, I will tell you that we do have a video on the transformers when I talk about grounding over on Fast Track's tube. There is a specific video I do. That's why I didn't want to get in it here, because I noticed the clock is clicking down, and I want to be good stewards of your time. Unless you have any questions that's germane to anything on transformers. But let's do a real quick recap when it comes to transformers. Okay, really quick. Let's see if I can do it here in less than 5 minutes. A recap for those coming in. All right. So if I have a transformer, let's just say it's a dry type transformer. I have a transformer. I have to have protection. Okay. If I'm dealing with a transformer where it is a single voltage, single phase output, okay, just one voltage is coming off, not like a 120, 240, just one voltage. If that's the case and it's single phase, then I can get away with primary only protection. And that will protect not only the conductors, provided you size them right, as well as the secondary. That can be done. Very unique. If it's a delta-delta unique situation, again, that is 240.21C1, very rare. But if I have that scenario and it's a 3-wire in and out and it's delta-delta 3-phase, then I can have primary only protection, okay, under 450.3b, okay? Most of the transformers you and I deal with, we're going to be dealing with primary and secondary protection. So you have primary protection for that transformer and subsequently the wires as well that can go up to 250% on the primary. I typically don't see that except for a feed application where you're going to have multiple transformers that could come on and have that inrush that really, as they're being used, could cause a problem with the actual protection, the feeder overcurrent device. So that's where you could go up to 250%. Other than that, I rarely ever see it. So you go up to 125% on the primary and to 125% on the secondary on most transformers that me and you'll be working with, okay? Now, it does go, and I have a video on this. Be aware that you have rules in 240.21c for C2, C3, C4, C5. That is your 10-foot secondaries, your 25-foot secondaries, your unlimiteds, and you have rules that you have to meet for the sizing of those secondary conductors, which are not taps. They're secondary conductors. So that is very different than what you would see for feeder taps in 240.21b. This is secondary conductors. Now, they may appear like taps, and people want to call them secondary conductor taps, but they're really just secondary conductor rules. And that's just for the conductors, okay? So those rules we didn't get too deep in, but I'm going to give you the quickest thing to remember. Whatever the size is of the secondary protection in the transformer and the panel or equipment you're feeding from that scenario, you better make sure that your secondary conductors are sized based on whatever the rating is of the device you're terminating into, the overcurrent device. Why? Because it says in 240.21c that you can't use the next size up rule, okay, when it comes to conductor. If it's not, you can't say, oh, well, can I use a 380 amp conductor on a 400 amp overcurrent device that's in the secondary? No, you can't. You have to have a conductor that's rated for 400 amps because that's what the conductor's terminating into, an overcurrent device. So it specifically tells you in 240.21c that you cannot use the allowance to go up to the next, to use a conductor that would be rated less than whatever the device you're terminating into. That does not come into play. You cannot use the allowances of 240.4 for that application, okay? 240.4b. Can't do that for those secondary conductors. So remember, whatever you're terminating those secondary conductors in, they have to have an ampacity rating equal to or greater than the device you're terminating it onto. Okay? So that, and you'll follow that in all the conductor sizes. So one morning, what we'll do is we'll have a session where we'll just do nothing but size secondary conductors from a transformer, if that's what folks want. And I think they probably do. All I wanted to talk about today was primary protection, secondary protection on a transformer. I didn't really want to get into the conductor sizing, but again, that just makes sense, right? If you're sizing the primary overcurrent protection at 125%, then I have to have conductors, okay, that are going to be sized and make sure that they are protected, right? That they are protected by that primary protection, okay? The nugget, yeah. So again, I try to cover a lot. Again, I'm going to have my haters who say, oh, you were all over the place, Paul. But let's let them try to do that live in an hour and be able to give you as much info as I can try to give you on the scenario that you might run into. It's not really exam prep. This is real world, okay, when you're dealing with 450.3b in the primary. So typically in the real world, you're going to determine what the KVA is a transformer. If it is a 480 volt transformer, the primary, you're going to use 831.36. If it is a 120/208 secondary, you're going to use the 208 at 1.732. That's going to give you the 360.25, or you can just use 360 and you'll get close enough. And so that's how you get the amps. And then you're going to apply 125% to the primary amps, right? And you're going to apply 125% to the secondary amps. Okay, and that type of thing. So now, the other little tip before I let you go is when I design transformer setups, I never pick the transformer until I actually know what the load calculation is for my secondary panel that I'm supplying. Okay, because it may change what that transformer can do, so or the size that I need. So always do a load calculation and know what's going to be placed on that transformer. Okay. And know that transformer's limitations in sizing and everything, and say, okay, so I got to do a load calc. I know everything that's going to be in my panel. Engineers should do this for you, hopefully, but if you have to do it yourself, do a load calc like you normally would for this panel. Forget that it's on a transformer. Forget that. Do a load calculation. Okay. So if I had to I want to bring you back here. Let me just, because I am giving you little tidbits that may be helpful for you. Let me take it back here real quick. Let's see if I can get, let's let's see, no, I don't want to do that one. Hold on, let's see, this one. Just for craps and giggles, I'm using this transformer. You want to make sure that in this panel that you're working, you have done an adequate load calc so that you know whether this 75 kVA transformer is going to work for you. Okay, if this 75 kVA transformer, this is a 12208, and we saw that the output in the device here is going to be 225, because again, that means this enclosure is rated 225, right? Remember we did this one earlier? This protects the panel board. That's required in 408, so you can't get away from it. So people ask me all the time, can I come and hit a panel with no breaker? No, not in normal applications like this. You're going to have to hit an overcurrent protected device, because you know what? If it's a panel board in here, that's the guts, then 408.36 is going to require me to protect this panel board. So for all intents and purposes, you're going to still have to meet that rule and have a breaker in there, okay? So if that case, this breaker is rated 225, then these conductors had to have an ampacity of at least 225. Make sense? And for those that say, where does it say that? Lastly, I'll just end up, because I have people out there that doubt me all the time for whatever reason. And again, they may not like my teaching style, and I go very quickly, and I may leave some people confused. I get it. You know, what we're going to look is 240.21. And I want to show you what I was talking about. We'll do these one day right here. Transformer secondary. Oops, let me share it. Transformer secondary conductors right here. All right. Notice this is what I told you right here. What does this say? It says 240.4b shall not be permitted for transformer secondary conductors. So what does that mean to you and me? All right. Well, if it's not permitted, that means that if I have a 225 amp device that I'm terminating those secondary conductors into, that's protecting that panel, those conductors have to be rated at least 225 amps, because I am terminating into that device, okay? All right? So hopefully that understand what it's talking about there when it talks about this right here, okay? Now, also you'll see that there's an informational note here that reminds folks about the overcurrent protection requirements for transformers. You know why it does this here? Because people can get confused in realizing that 450.3 is about protecting the transformer. Yes, it may also protect the conductors if you follow the rules here in 240.21c. They may be able to do both. But what I can promise you is if you go to the maximum 250%, it may not protect the conductors, even if you size it based on 240.21c. So that's why you have to understand the different rules and say, well, look, I protected the transformer. If I went up to 250%, I got to make sure that I'm still protecting the conductors. And so, you know, that's why our code it's difficult. Okay. I joke about plumbers, hot on left, cold on right, crap don't run uphill. Well, when it comes to electricians, these are little nuances that you need to be aware of, and you just don't get locked into one thing, right? You don't get over there in 450.3 and think, okay, this is going to cover everything. No, that only deals with the transformer protection. You still have to go look at the secondary conductor protection, right? And when you look at that, the protection for the transformer may not provide adequate protection for the conductors. So that's why most people that design these will not use a 250%. If you're doing just a single transformer, for example, and you're not doing like a feeder with multiple transformers, which the 250% seems plausible for that. But when you're just doing single transformers, most people just go what? 125% primary, up to 125% secondary protection. If it doesn't correspond, you use note 1 and just go on your merry way. Next, primary side, you need to make sure those conductors are sized based on the amps that it could see, all right? Which again, in that case, let's say it was a 225 amp primary protection, then I want conductors that are good for 225 amps. On the secondary side, I know what they're terminating into. I can save myself a lot of math and say, well, if those secondary conductors are terminating into a 225 breaker, then I'm going to make sure those conductors are rated for 225 amps. Done, right? But you do have some other allowances and some other rules for conductor sizing in those secondary conductor rules, the 10-foot rule, 25-foot rule, things like that. We will cover that in another episode. But if you can't wait, then there is a video available over on Fast Tracks Tube. If you're a subscriber, you can watch me actually do that in a multi-part series on transformers. Okay. All right. I went a little over today on coffee hour. Hopefully you got something out of it today. Hopefully I didn't jump all around and bore you. Again, this is a new format, and I was a little rushed today because if you remember, I wasn't going to do a live session until Thursday again, but I decided at the last minute, let's go on and get it done. So, folks, take care. God bless. Hope you got something out of it, and give us the feedback. Again, if you want to be nasty, go on. You don't need to watch my stuff. I don't have no desire for nasty people. If you got something out of it, I appreciate it, and share it with others. If you didn't like it, do me a favor. Unsubscribe and don't watch me. You won't hurt my feelings, okay? But those that do enjoy it, I appreciate you. Take care. God bless.